Okay, so we're going to launch into our an investigation now of magnetic materials, and we're going to parallel the development that we followed in our consideration of dielectric materials. So I'd just like to remind you of how we approached the problem of dielectric materials. Okay, so our thought in developing dielectric materials, or the theory, was that a dielectric material is a material that is comprised of molecules that carry a dipole moment or that can be polarized, and that in the absence of an electric field, so that's this upper plot here, those dipoles are randomly aligned. If we apply electric field, however, so this field is applied to this lower plot, those dipoles line up and we get a dipole moment per unit volume. You'll notice that we tend to get plus charges down this surface and minus charges down this surface, and this is in fact the origin of the surface charge density that we discovered when we studied polarization in dielectric materials. Okay, so this was the the basic model that we followed in dielectrics. Now, when we study magnetic materials, we're going to follow a very similar line of thought. So our procedure then is the following. Okay, so very similar idea. We're going to consider a magnetic material as one which is comprised of a whole lot of little magnetic dipoles, and each of these, if you like, could be considered as a little current loop. Okay, in the absence of a magnetic field, these dipoles are all randomly aligned. When we apply a magnetic field to the material, as described here, those dipoles will line up. So in other words, the game here is exactly the same kind of game that we played in our development of electrostatics. In electrostatics, we generated volume and surface charge densities, and in magnetostatics, we're going to generate the possibility of volume current densities and surface current densities. So based on the model of dielectrics that I presented on the first slide of this segment, we developed the following theory of dielectrics. Okay, so here we have a dielectric material, this red blob. We've identified a little volume element, P, the P D3R prime, so this is the dipole moment per unit volume multiplied by the little volume element. So this has units of this is a little electric dipole. And we ask the question, what is the contribution to the potential at location R due to this element at R prime, and then we integrate it out over the material. And that's expressed by this equation here. So this is the potential at R, this is the potential at R due to all these little dipoles, and this is our formula for the potential due to a dipole. With some fairly straightforward mathematics, we recast this expression in the following form. Okay, so what we have here, if you'll remember back to electrostatics, is we identified the dot product of the dipole moment per unit volume with the surface normal n hat, that's this n hat, it's the surface normal. This becomes a surface charge density with units of coulombs per square meter. On the other hand, this term here, minus the divergence of the dipole moment per unit volume, becomes a volume charge density. Our procedure in developing our theory of magnetic materials will then follow a similar kind of direction. Okay, so this then is our starting point. We consider a magnetic material with a magnetic moment per unit volume given by m. If we multiply that by the volume element, d3r prime, this little volume element, we get units, we get the dipole moment of this little differential contribution here. And then we ask the question, what is the contribution of this element to the vector potential A at position r? Once we know that, we integrate over the full material, and our expression then for A at r becomes the following. Right, so this is the m times d3r prime is the dipole moment. This is the r prime is the location of the element, r is the location of the point of observation, and we divide by the square of the distance. Okay, so just as in our development of dielectrics, we did some fairly straightforward mathematics and were able to recast our dielectric equation for the potential in terms of a surface charge density and a volume charge density, we can do some straightforward mathematics on this equation, and we can recast it in terms of a volume current density and a surface current density. And that goes through in the following way. Okay, so all I've done here is I've rewritten 1 on mod r minus r prime squared in the previous equation as the gradient of this function here, gradient with respect to the prime coordinate. And you'll notice that this actually looks rather like this looks like we should do some sort of integration by parts to recast this equation. And the reason I say that is that we might, in our integration by parts formula, identify this bit here as maybe our u term and this bit here maybe as our dv term. And we know when we integrate by parts that the integral of u dv is equal to uv. Okay, so this is the one-dimensional form of integration by parts. This is a three-dimensional equation that we have to deal with, but actually it's rather similar beast. And we are indeed going to integrate this thing by parts with the identification that I've written here. So let's do that and see what comes out. Okay, so if we were to do that integration by parts, of course we must generate a term that looks a bit like this. This is our surface integral term, a term of one lower dimension than our original integral, and this is our volume integral term. Now I've been pretty quick with how I've done this. I know that I have to combine m with some other vector to create a vector quantity, and really the only one that I can do this with is the surface normal. So I've written this as m cross n, and I know when I take the derivative of the m term, I have to take a vector and I have to return a vector. So really the only tool that I have available to do this is the curl, and so I've written it like this. Now this is really just an argument that it must be of this form, and if you want to follow the full derivation through, I encourage you to do that. Integration by parts, we might expect a minus sign here. In this case, in 3 dimensions with the curl, if you track it through, you in fact get a plus sign. Okay, if you look at this, you'll notice that this term here looks like the contribution to A due to a surface current, m cross n, and this looks like a contribution to A due to a volume current, curl of m. And so we make the following identifications. All right, so if we know the magnetic moment per unit volume m, we can calculate the bound surface current by taking its cross product with the surface normal vector n, and we can calculate the bound current density, volume current JB, by taking the curl of m. And this, as I have argued, is really very analogous. It's directly analogous to our development of dielectrics. In dielectrics, of course, we didn't discover bound currents, we discovered bound surface charges and bound volume charges, but you'll notice that the development is very, very similar.